In all fields, you tend to find there's this tendency to have a separation between, what's relevant in the field for the industry and, what academics like to work on. It's very difficult for people who are involved in kind of day-to-day operations in a company to have the time to step back and really analyze, what are the research needs. It's simply not possible for any one company on their own to really do the sort of research we're doing. And similarly on the academic side, now because one sees the need to combine results from a large number of different characterization techniques, this means that no one academic group can really bring all the aspects to the table. So on both sides, the industrial side and the academic side, I think you really need to get this leverage that comes from having many different institutions working together. By working on a pre-competitive level, we can progress the basic science, and then the basic science can be used by the people in the industry to come up with a whole diverse range of new products. And this also means that you get much more in the end for the investment. It maybe takes longer time, but rather than focuses energy specifically on one solution, you're really spreading your bets and saying, okay, we think that this can progress in a whole load of different fields, and we don't try and keep it secret. We try to work in a kind of way of open way so that anybody can really pick up these fundamental findings and use them to support their new products. I say all the time that people really undervalue concrete. If this material was developed now, it really would be a miracle. And it's almost a sort of coincidence of nature that by taking the most common raw materials on the planet, you get something that can work just by simple mixing with water and react at room temperature with almost no volume change. I mean, there's no other material that really can do that. So it's quite miraculous. Now, the focus really comes from the question of environmental impact. So, concrete is actually a very environmentally friendly material. We see that it has a low intrinsic energy and CO2 per ton. But in terms of the very, very large volumes used, this means it all adds up. But that's also why by doing research, this research can have a very large impact. I think it's important to realize that, modern infrastructure would fall apart without concrete, and at the end of the day, people need houses, they need roads, and generally when you look at these kind of structures, the most efficient way to build them both in terms of energy, CO2 and resources is in concrete. But then we can look further, we can look at, what are the ways we're going to produce energy in the future. Hydroelectric power is a very important renewable resource. Here in Switzerland, it makes up 60 to 70% of the electricity, and that's all produced. This would not be possible without concrete dams. We see wind power becoming an increasingly important solution, and there the foundations are always in concrete. So, I mean, there's a lot of, we really need concrete. We couldn't do without it. So we have two types of projects, which we call core projects and partner projects. And it very much goes back to this idea of partnerships that, of course, the industrial partners are putting in cash to the network, but the academic partners already come with their own research. So they have their own independent research outside Nanocem. This is part of the richness we can bring through this virtual network. And then we analyze in great detail what the different people are doing, and therefore try to identify the gaps and where we can go beyond what individual people are doing. I think that's also very important, because what I see going around the world is there's an incredible amount of duplication. somebody reads some idea, oh, we'll work on this cement, and then you have 100 other universities around the world which do a PhD in exactly the same area, and you know, that doesn't really, it's not very, very efficient. So in Nanocem, we do exactly the opposite. We really try and look what's already been done and then say, where can we go beyond it? So it does take us quite a long time to design our research, but in the end, I think it has much more value, and it really goes into areas that can only be tackled in this way, that really would never be tackled by individual small research groups. The industry are very, very strongly implemented at all levels. I mean, first of all, by helping to identify, you know, where the real gaps are that will have a significant impact in the field. That's the first thing, because I mean, you know, with a complex material like this, there's almost an infinity of things you could look into, and you have to prioritize that. And of course, you want to prioritize that according to what can really make a difference in the field. So that's the first level. Then, of course, many of the people in the industry, I mean, they're researchers as well. So they bring to us a lot of prior knowledge that often is not published. Particularly, you know, I mean, industrial people, they'll try a lot of things, they'll see what works and what doesn't work, but that will never get published. But then when we set up a project, they'll make that information available to us. And that can often mean that you sort of save 1 or 2 years in your research project before you even start. And then while a project is running, we have very regular meetings, you know, generally every 6 months per project, where typically 3, 4, 5 people from the industry are coming and commenting on the work. And this also means that you really get a good focus, you avoid going up dead ends, and it's also very good for the students because it really takes another level in terms of what they have to do in presentation of results and discussing with the kind of client, in inverted commas, which are all skills that then I think will stand them in very good stead later on. Bringing a thermodynamic approach. It sounds trivial, you know, thermodynamics is the basis of all physics and chemistry, but it tended to be treated rather superficially in the cementitious field, again, because of this complexity. And when you have complexity, it means that the methods you have to use are slightly more difficult. So, you know, through our very first core project and developing a new model for looking at the phases that formed on hydration, this has now become a sort of standard reference for all projects. And even beyond Nanocem, it's being used on an everyday basis, both in the industry and in the academic side. So, I mean, I think that's a highlight. Now, then, okay, that still sounds very fundamental, but what we can see is that indirectly from that approach, we are influencing the kind of standards that are now being drawn up for new cement types. So, for example, we could show in this first project that if you took limestone, which is very, very cheap, very available, and has no, if it's not heated up, it has no CO2 emissions, we could take that limestone and rather than just acting as something inert, this would actually react a little bit in the cement. And by understanding how and why it reacts, which is determined by thermodynamics, you can then find ways to make it react more, which means you can put in more limestone, and every percent extra limestone you put in is effectively a % less CO2 you produce. And that's now filtered through, that there's now a norm being discussed in Europe for combined additions of limestone and the common supplementary cementitious materials like slag and fly ash. What's clear is that we've managed to do an awful lot with really quite a small amount of money. And it's not like I'm trying to tell you we need billions and billions to solve the problems. Just the opposite. What I'm trying to tell you is the incredible progress we've made in understanding the fundamentals in the last 10 years makes it clear that we can solve these problems and solve these problems for a relatively modest investment. but we do need some investment. We can't do it for nothing. Yeah, I think that's the other point I like to highlight is, the work we've done on nuclear magnetic resonance and pore structure. That, I mean, this was a technique that was out there before we started Nanocem, but it was like something of a scientific curiosity. So, there'd been quite a few publications over the last 20 years, publishing results, and everybody said, oh, this is great, but so what? What does it mean? And going from oh, this is a nice result to actually, what does it mean and what can we do with it, was really a long process, and a long process of engagement between, people working, as physicists and people working as material scientists and the industry. And now we really have brought this technique to the point where it can be used on a routine level. It gives us a quite significantly different vision of what the pore structure really is compared to what we thought before. So it's really brought up somewhat of a revolution in our thinking about pore structure. And then, of course, that then indicates where we need to go in how we can control the hydration process, how we can control the kinetics, how we can, in the future, lower CO2 emissions. It all comes back to the same thing in the end.